Good afternoon, everyone, and a very warm welcome to NV's webinar series on the LiFE program, was hosted by IISc EIACP. Today, as we approach the World Atmosphere Day, we are shifting our focus to the vital role of the atmosphere in the sustaining life under the Lifestyle for Environment initiative. So, as we all know, this LiFE program introduced by our Honorable Prime Minister Narendra Modi ji during COP26 in 2021 advocates for a sustainable lifestyle that prioritizes mindful utilization over wasteful consumption. This initiative encourages collective action to adopt the climate-friendly practices in our daily lives. The LIFE program recognizes individual actions when multiplied across the global population can have a very significant and positive impact on the environment. So today we are focusing on the critical importance of our atmosphere, a dynamic system that sustains life, influences our climate, and faces increasing pressure from various anthropogenic activities. Now I'd like to call Gagana to introduce our speaker.
Good evening, everyone. We are delighted to have with us today Dr. Durga Mahapatra, Associate Professor from Department of Chemical Engineering at the University of Petroleum and Energy Studies, Dehradun, India. He is an expert in environmental bioprocesses, focusing on the water, energy, and food nexus. Dr. Mahapatra aims to provide regional sustainable development solutions through green technology and optimal resource utilization. Today, he will be sharing his expertise on the crucial topic of atmospheric well-being, that is carbon capture, utilization, and storage and beyond. This discussion is particularly relevant as we strive for a healthier planet and explore innovative solutions to mitigate atmospheric challenges. So we encourage you to actively engage with Dr. Mahapatra's insights and participate in the question and answer session following the presentation. Now, please join me in warmly welcoming Dr. Mahapatra, sir. We welcome you, sir.
Thank you, Dr. Tulika and Gagana. Thank you for the introduction. We had the World Atmosphere Day on 10th of April, and I'm glad and really fortunate that I have been invited for this particular topic to be addressed, which is very critical from a national and an international perspective. Here we will be learning about the present state of the atmosphere, that is atmospheric well-being. So what is actually the health and the status of the atmosphere today. We'll be also brushing our concepts on carbon capture, utilization and storage, and we'll look at the frontiers of carbon capture technologies, the way it has been utilized, and through fuels, polymers, fertilizers, and so on and so forth, how are we catering to the requirements of the consumers at various levels through a sort of a stakeholders involvement. And we look beyond for the open horizons to be worked upon, the carbon capture and storage technologies for a really vibrant and a zero emission future. For this, let's have an understanding of atmospheric well-being. So here in this case, so this is mostly to do with the health and the stability of the Earth's atmosphere as we have been witnessing. So there have been a lot of factors that are driving the atmosphere, be it indoor and outdoor air quality, climate stability, the presence of greenhouse gases. Everything impacts the atmosphere, and therefore for sustaining life it becomes pretty much crucial in maintaining an ecological balance and maintaining the status of atmosphere. So here, as we move along, we would also get to learn about how do we ensure atmospheric well-being that involves a continuous monitoring and managing these factors that I just told, that would help us to prevent adverse effects on human health, ecosystem, and the global climate. Now let's look at how are we going to address such concerns. So these are some of the importance of why do we go about addressing the carbon emissions. Firstly, climate change mitigation. It helps to slow down the global warming, mitigate the impact of the climate change, where we are encountering these days, compounded extremes of weather events. So when we say that, It is, to give an example, in the Himalayas, we have the avalanche. Now, this avalanche could be a rock avalanche and or an ice avalanche. So if it is compounded by a cloud outburst, then it could be catastrophic. So in this case, there could be compounded extreme weather events that might be responsible for the global changes that are being witnessed today. It could lead to a rising sea level. It could be leading to a loss of biodiversity and so on and so forth. Secondly, for our health benefits, it is recommended that we should have lesser respirable and non-respirable particulate material, which is RSPM, PM2.5 and PM10. So lowering carbon emissions as well as the particulates can improve air quality that reduces respiratory and cardiovascular diseases that is caused by the air pollution. Well, when we are having a better atmosphere, that also ensures that we have a greater economic stability. So as we are transitioning to low carbon technologies and practices, so this actually has created new avenues for economic opportunities that promote sustainable development. And this on an edge would help us reduce financial risk associated with the climate change disasters. And finally, environmental protection. So here, the moment we say that we have carbon negative technologies, carbon neutral technologies, we have lesser emissions, lesser particulates, this reducing carbon emissions and the other air pollutants would help us preserve natural habitats and therefore would protect wildlife and maintain the very integrity of ecosystems. So here, we actually are more concerned about reducing carbon emissions that enhances the atmospheric well-being, that ensures a healthier and a more sustainable future for all. Now let's make ourselves familiar with CCUS. As you know, CCUS is carbon capture, utilization and storage. If you would have heard very recently, there have been back-to-back talks and deliberations on opportunities for CCUS in India. So these are technologies that are destined to reduce carbon dioxide emissions from industrial and energy-related sources. So this encompasses three stages: the carbon capture stage and the utilization stage and the storage stage. We will get into the details of this in the later slides. So let's see how we have witnessed carbon emissions in the atmosphere. So to give you a brief history of how does it all happen, way back in 1972, there was the first large-scale carbon dioxide injection project that began with Sac Rock. So this is actually an oil field in Texas in US, and this was mostly propounding enhanced oil recovery. So these are some of the major milestones where we could actually dream about large-scale sequestration of carbon, capture and sequestration of carbon. Some of this could be very well, where the carbon dioxide is into the geological, is pushed into the geological strata. 1996, we have this Lipino project in Norway that became the first commercial scale carbon dioxide storage project. Here, this entailed injecting carbon dioxide to deep sea saline aquifers, which is beneath the North Sea. We are taking up these cases also in the later slides. And then we have the Global Carbon Capture and Storage Institute that was established. And this was done to promote development and deployment of carbon neutral technologies or carbon capture strategies globally. And recently, we have witnessed a surge of CCUS projects worldwide, with over 700 projects in various stages of development. This is as of 2024. And this particular financial investments, participation from stakeholders, intervention from government reflects increasing recognition of these carbon capture and utilization and storage technologies. And it might so happen that they can play a critical role in achieving the net zero emissions by mid-century. So this particular figure gives us the various ways in which we can actually have carbon capture, utilization and storage at different stages. So here at the center, we could see how the things are getting pooled together as resources. And in the peripheries, we could see the different entities that are used today for capturing carbon, the way it is sequestered, the way it is stored. So we'll be getting into the greater details in the later slides. Now, why is that we need carbon capture, utilization and storage? It's pretty much eminent. pertinent to these figures that have been put forward. So if you look at the type of the carbon emission statistics here, the annual emission in 2024, you could see the global carbon dioxide emission from fossil fuels and industry reach astounding numbers of around 40 billion metric tons. So that's the type of the emissions that we have. Historically, if you have witnessed the increase, so since 1990, we could see that the carbon dioxide emissions have increased by more than 60%. Now, let's look at the major countries, the major contributors to such emissions. Undoubtedly, China and US have contributed to the maximum. So we really cannot blame it onto us. It's because we are the single largest country which is developing at an astounding rate, where the per capita carbon dioxide emission is pretty low here. We stand at the 19th position in per capita carbon dioxide emissions compared to the fastest developing nations. So in this case, China and US have contributed significantly to the carbon emissions, where it is 450% since 1990. However, US, because of strategies, have dropped down around 6% of the carbon emissions very recently. Now, as per records, the global average atmospheric carbon dioxide concentration has reached to a new record, which is greater than 425 ppm as on 2024. So this is a pretty high compared to the values that we have witnessed in the last 2 decades. So what does that show? That shows a need for better technologies, better carbon capture, so as to reduce emissions. Now let's look at some of the impacts on climate change. Well, global warming, the increased CO2 levels have trapped more heat in the atmosphere today, that is leading to a rise in global temperatures. And this phenomenon is actually called the greenhouse effect. You have extreme weather events, as we just discussed. So higher temperatures have contributed to more frequent and severe weather events. So that there are outcomes, like there's a lot of catastrophes like hurricanes, heat waves, and a heavy downpour, which is because of untimely rainfall. These are some of the compounded weather extremes. We have also noticed a great deal of sea rise level. Melting polar ice caps and glaciers are today driven by global warming, and that has caused sea rise level. And therefore, this has altogether threatened the coastal communities and has actually impacted the pretty microhydrology of the regions, where there are salinity innovations into the land masses and so on and so forth. So there are a lot of critical implications to these. And you have the very disruption of ecosystem. Ocean acidification being one of the things, where the ocean absorbs a significant amount of carbon dioxide that leads to acidity, and this acidity has led to coral bleaching, a loss of aquatic biodiversity, great deal of losses in aquatic farming, and so on and so forth, in marine life, and so on and so forth. And finally, we have this ecosystem disruption, where this is being witnessed is because of a change in temperature and precipitation pattern. There have been very frequent disruption of natural habitats that has affected biodiversity and has led to a predominant loss of species in Asia and abroad. So this particular graph actually gives us a very idea. So this is collected from Bloomberg, where it shows the proposed carbon capacity which is to be installed. Because of this need, we need to make sure that we actually compensate for the pollution that we make up from the fossil fuels for 420 million tons per annum. So which is a huge investment of around $6.4 billion, where so the market is going to be US and other European countries. And if you look at the breakdown of this, so from 2020 until 2035, you could see that how there has been an increase in the amount of the carbon dioxide, and these particular colors are representing to various sectors where this is going to contribute upon the global capture of the carbon dioxide, where there could be different entities like ammonia, hydrogen, power generation, natural gas processing, oil refining, cement production, ethanol production. So these are the different sectors that have significantly contributed to the carbon dioxide rise, and therefore this needs to be dealt on an urgent basis. Now, when we say carbon capture, what do we understand? So carbon capture is predominantly divided into 3 stages. the pre-combustion one and the post-combustion and the oxy-fuelants. Uh, uh, for the paucity of time, I'll be not getting into the details. So, however, these particular figures are not to confuse people, but to make sure that they at least have a notional view of the various characteristics of the carbon at different. So, pre-combustion is mostly removing carbon dioxide from the fossil fuels. So, FF is fossil fuel. So, there are a little bit of uh, uh, disruption in the subscript and superscript, maybe because of the fonts that might not be tallying. So here we have carbon dioxide from fossil fuels before they are burned, which is the pre-combustion, where if the carbon dioxide is captured from flue gases after the fossil fuels are burned, this is the post-combustion capture. And then we have oxy-fuel combustion, where while burning the fossil fuels in an atmosphere of pure oxygen, here we actually are capturing carbon dioxide. So there are various, so I would not spend a lot of time on this. So gasification, where fossil fuels such as coal and partially oxidized into high temperature, pressure environment to produce a mixture of gases, which is mostly syngas. And this syngas is actually constituting of hydrogen, carbon dioxide, carbon monoxide, and other gases. So these are some of the fuels that could power heavy machineries. So water gas shift reaction is a very famous reaction. So here the syngas undergoes a reaction with steam to convert carbon monoxide and carbon dioxide with the formation of additional hydrogen. So there's a benefit to it. And then you have CO2 separations. I'm sorry for the subscripts, that is the fonts here. CO2 separation, of course, here the CO2 is separated from hydrogen-rich gaseous mixture using physical and chemical absorption methods. So if you look at this pre-combustion stage here, you could see that before the combustion even happens, the carbon dioxide is captured in between. So the post-combustion is where we see that the carbon dioxide getting captured from flue gases. So this is flue gases which are treated to remove impurities such as sulfur dioxide and nitrogen dioxide. So flue gas treatment is being done. During this, we could actually take out carbon dioxide. Carbon dioxide absorption happens. So here the treated flue gas is passed through a solvent. And usually what we have proposed is a variant of ammonia-based solution. So we have applied a new technique and we have just applied for a project to the ministry, which applies to a variant of ammonia-based solution that could, scrub carbon dioxide through columns. And then you have the solvent regeneration technologies, where the carbon dioxide solvent is heated to release the captured carbon dioxide. And this is then compressed for transportation and storage and so on and so forth. So this is the ways in which we can capture carbon post-combustion. Oxy-fuel is very interesting. So this involves burning fossil fuels in an atmosphere of pure oxygen instead of air. So here we need to maintain an oxygen concentration, which is very pure. This process produces flue gases that is mostly to do with carbon dioxide, water vapor, and it is having less proportion of SOx and NOx. So here it involves air separation, which is oxygen separated from nitrogen in air using air separation units. We have the combustion, where fossil fuels are burned in the presence of pure oxygen, producing a flue gas with carbon dioxide concentration. And finally, we have this flue gas treatment, where the flue gas is cooled to condense, water vapor, and then the carbon dioxide is left behind that can be captured and stored. So these are the schematics for each of the stages. Then comes carbon utilization. When we say carbon utilization, it could be directly conversion to fuels, to feedstocks, and to building materials. Now here, it is very interesting aspect to see that what are the different ways in which we are able to, capture the carbon dioxide and use it. So this use can predominantly make us less burdened, where we are cutting short imports. Now we are spending millions of dollars on imports of oil and natural gas and polymers. So it could get we could cut short this. So conversion of fuels is pretty much important here, where carbon dioxide can be converted to various types of fuels through chemical processes. It not only helps in reducing carbon dioxide emissions, but also provides an alternative source to energy. So these are some of these key methods. Synthetic fuels, CO2 can be converted to synthetic fuels as methanol, ethanol, and synthetic gasoline. And here, if you look at, it helps in reduction of carbon dioxide emissions. And these fuels can be used in existing engines and infrastructure, making them a practical alternative to fossil fuels. Now, biofuels, I'll be elaborating on some of these aspects later, where we will be talking about algal biofuels. that we have been uh, growing through a concentrated stream of carbon dioxide in wastewaters and provisioning it for further capture of flue gases. Chemical feedstock like urea, polycarbonates, and other chemicals could be also formed. So today, urea is a key component of fertilizers, and we are looking forward to having a lot of carbon getting used up from this type of process. You have polycarbonates, where CO2 can be used to produce this type of polymers, which is used in a wide range of applications using electronics. And then you have alternate automotive parts and construction materials. So polycarbonates is being in this. And then you have other chemicals which like formic acid, acetic acid, and dimethyl carbonate, which can be converted to other forms. So these are some of the things which can be used as a feedstock or as a starting material or a precursor to a number of different types of polymers. And then we have the building materials, which is where we have to see that this carbon dioxide that can be incorporated into building materials, mostly to store carbon permanently, where it enhances the properties of these materials. You could have examples of concrete where carbon dioxide can be used to be integrated here, where it reacts with the calcium compounds to form stable carbonates. This process does not sequester carbon dioxide, but also improves the strength and the durability of the concrete. So there are a lot of research and development being done at an Institute of Science and many other places, where we have thermal comfort and a lot of other characteristics that will be imparted when you pour in carbon into such type of building materials. And then we have also the carbon negative materials. When we say that, it is some of the processes where we create carbon negative building materials that lock carbon dioxide permanently. These materials can be used for production of cement, plaster, and other construction products. So this particular figure would actually give you a way of catching up carbon. So one of the ways is chemically catching up carbon. The other way is actually catching up carbon with biomasses through photosynthesis. So there could be different types of processes like electrochemical processes, which should be integrated from the renewables, where you can have a lot of carbon fixation. And there could be also processes with plants and algae, where because you use a lot of systems understanding, systems biology, we can use bioreactor engineering, and then we could actually produce a lot of fuels and plastics and polymers and so on and so forth. So the sources of these figures have been mentioned below. Now let's look upon carbon storage. So it's one of the most important aspects here. If we are at all dreaming of sequestering or storing million tons of carbon that is getting generated from industrial processes, it is through the investigations that are being done day in day out relentlessly for exploration of possibilities of carbon storage. So here we talk about geological storage, which involves injecting carbon dioxide into deep underground rock formations. So these formations can secure carbon dioxide for thousands of years. So there are many types of geological storage. We'll be dealing with the depleted oil and the gas fields, which is where they have already trapped hydrocarbons for millions of years, and now this is a possibility of making it suitable for carbon dioxide storage. So additionally, CO2 could be used for enhanced oil recovery, which we are going to look at in the future slides. So deep saline aquifers, so these are porous rock formations that are filled with salty water. So here they have large storage capacities which could be widely used to sequester carbon. We have this unmineable coal seams. That carbon dioxide also could be injected to such type of seams that have not been economically very viable. We actually get a lot of out of open cast and other mines. We could actually see a lot of coal that are not very much feasible for further processing. In that cases, this coal seams could be the coal seams that looks uneconomical could be used for this purpose. The carbon dioxide get absorbed over the coal, and it displaces methane, which is one of the important aspects, and that is what is the starting point for a new field, which is called the coal bed methane. So CBM, where there is a possibility of extracting a lot of methane and a possibility of again putting carbon dioxide, which is getting to be absorbed over this coal particles or the coal surfaces. Then we have this ocean storage. So here we could actually see that this involves carbon dioxide injection into deep oceans, where we are expecting that this remains isolated from atmosphere for at least centuries. So we have this direct injection where carbon dioxide is injected directly into the ocean, where it dissolves and forms a stable layer at the ocean floor. And it could be an ocean fertilization. So here it is very interesting. This method involves adding a nutrient to the ocean to stimulate the growth of a lot of algae, which are called phytoplanktons. And this absorbs a lot of carbon dioxide through photosynthesis. And therefore, when these algae die, they sink to the ocean floor, sequestering the carbon. So we have already reported such type of instances where diatoms have become significant sources of such type of fuels deep down in the ocean sediments, which we have reported as a publication way back in 2009, where diatoms have been looked at as prospective feedstocks for production of oil. Mineralization, a very important component, is the process where carbon dioxide actually reacts with naturally occurring minerals to form stable carbonates. So this is a method that offers a permanent storage, and therefore it could be integrated into the production of building materials. Now we have a natural mineralization process where carbon dioxide reacts with magnesium and calcium silicates to form carbonates. So this process occurs naturally, but it could be accelerated through engineering processes through catalysis. We have industrial applications where carbon dioxide and minerals actually react, and then there are the formation of stable carbonates. Now this reacts with minerals to form these type of carbonates that is then locked away as into concretes as CO2. So here we actually look up at typical ways of fixation through the mineralization process. So these are some of those representative schematics where you could see that how different earth, so the stratas of earth could actually give us an idea about the carbon rich layers that have been looked at from the top. So you could look at the various layers here, and these layers correspond to different aging patterns of the soil, where that could be predominantly a carbon that gives us an idea about and such type of stratigraphy and methodological approaches would help us discover more into how do we put in a lot of carbon dioxide into these type of basins. So this is a schematic for the, so here it could be these two different types where you could push it as a nutrient for algae, or it could be also getting settled at the bottom. And then we have this very process of mineralization where we have the calcium carbonate getting formed, the magnesium and calcium silicates forming carbonates, and so on and so forth. Now, having a know-how of utilities as in capture, utilization, and storage. Now let's look at the different aspects of carbon capture technologies. So here we have the direct air capture. So here this extracts carbon dioxide directly from the ambient air, and this process involves chemical or physical processes to capture carbon dioxide, and therefore it could be then stored. As a process, air is passed through a filter or a liquid solution that binds to carbon dioxide, and it directly is then forming a carbon dioxide concentrated stream. The carbon dioxide is then separated from the filter or solution using the head. So here such type of reactors would help in having a concentrated carbon stream. So this is the process where we can use direct air capture. You could see in places that are installed. So here air is vented into this. They are into a solution. So this is a chemical or a physical mechanism of capturing carbon dioxide. They're concentrated, and then they could be routed into utilities or storages. So applications could be that the carbon dioxide used for various processes like synthetic fuels enhancing agricultural productivity, or it could be then stored in geological formations. However, there's a lot of challenges wherein, so these processes becomes highly energy intensive, is because you need to keep these things active for the entire time. And so where we have very less percentage of carbon dioxide in ambient air, it really takes a long time and a lot of effort to concentrate to that level where it could be sequestered and stored. And then such type of technologies need to be developed where it is made inexpensive. Now we have the bioenergy with the CCS, which is called the bioenergy with carbon capture and storage. Here, there's an option for capturing carbon dioxide from such type of processes where it could be generating bioenergy. At the same time, there is a provision for storing it underground. So here this could be, the biological ways like fermentation, aerobic oxidation, or it could be the thermochemical ways of combustion, pyrolysis, or gasification, where such type of things can be used, where the carbon is captured and stored in as into geological formations, or could be right away used for fuels and polymers. However, we have challenges with it. We need to see that there is a persistent availability of biomass, and there has to be a reduced cost of capture and storage. So these are some of these places where there is a large scale growth of biomass, algae, which is already happening because of a lot of dissolved carbon which is there in the various water systems in cities like Bangalore. So here you could see that this have resulted exploration of such type of algal biofuel projects that have come up very recently. Then we have this enhanced oil recovery. So here in this particular process, we could see how these have resulted in extraction of additional oil from depleted oil fields by injecting carbon dioxide. So here, this is pretty much important here, is because this process helps in injecting the carbon dioxide into the depleted oil fields, and this helps in a faster rate of oil recovery. And here in this particular process, as you could see, this method of extracting additional oil would help in increasing oil recovery and also a lot of carbon dioxide sequestration. So process is pretty simple. Carbon dioxide is injected into an oil reservoir where it mixes with the oil, and when it mixes with the oil, it viscosity and makes it very easier to be extracted. Now, this has been very rampantly used in industries today, and this is widely used in almost all oil industries to extend the life of the oil field and increase the production rate. However, there are challenges where one has to deal with higher although its promise is higher carbon dioxide storage, but this also promotes a lot of extraction and use of fossil fuels. So this enhanced oil recovery is mostly to promote more extractions of this. So this is given by this particular diagram, where you could see these are the vents through which carbon dioxide is pumped in. This is the injection pump here, and then so there is a mechanism where this carbon dioxide goes to these places, and it's actually pushes oil, and then the oil is dragged with the help of carbon dioxide, and the spent carbon dioxide again pushed back through a compressor into this. So it's a continuous cycle which enhances the oil recovery. Now let's take up certain cases here. So one of the most successful cases is the Northern Lights project. You might have all heard about the Northern Lights. Everybody wished to go there at once in a lifetime. So this Northern Lights is actually in Norway, and this Northern Lights project is an initiative from Norway, and is a pioneering carbon capture and storage initiative. So this is the world's first cross-border. When we say cross-border, it is across nations where the gases could be transported, and then it has to be stored in the facility. And this is designated to capture carbon dioxide from most of these industrial sources. And this is transported via ships, as you could see here. And then it is stored permanently in geological formations beneath the Northern Sea. So here in this particular figure, you could see where is the place. So places from all these areas is where the gases are collated together, and then it is shipped to this northern island, and beneath which it is stored. So this is a cross view schematics where you could see the capture and the transport. And so when we say CTS, it is capture, transport, and storage, and this is being done in oceans. So this type of carbon dioxide capture helps for a better industry collaboration with organizations, where they could actually have service sectors getting involved, wherein the carbon capture, transport, and storage could actually happen simultaneously. And this is being done with the help of top tier industries like Equinor, Shell, and Total Energies. Microsoft has also promised to be a part of it, where all its carbon dioxide emissions in its plants also could be routed to this. And this is the part of this Norway's broader Longship CCS initiatives. Now let's look at some of these achievements. So if you look at the achievements here, this Northern Lights project became operational in September 2024, and this has made a significant milestone in the CCS efforts. Now today, as on March 2025, the project is where we have 7.5 billion Norwegian currency is invested to expand its injection capacity from 1.5 million tons to 5 million tons of carbon dioxide per year. So this is the type of scale. If you look at the type of agreements that are made, this project has secured the world's first commercial agreement for cross-border carbon dioxide transport and storage. So with Yara International, you might be already knowing, this is a major fertilizer company. So there are agreements made. So this is one of the mammoth tasks that has been taken today. However, this also encounters a lot of challenges. So these are challenges in terms of economic viability, where the project relies heavily on government subsidies and the financial support to remain successfully viable. So therefore, there is a high cost for capture, transport, and storage, and this has of late become very significant. Now, there are also logistic complexities where transporting CO2 via ships involves a lot of logistic challenges, like you have limited docking opportunities where there's so commodities which awaits a lot of docking. However, so therefore there are higher shipping costs when you are transferring this type of gases. So these are some of the challenges with logistics, and scalability being the most important issue. While the project is actually a significant step forward for scaling CCS, but the problem here is that to meet the global climate targets, it has to overcome the technical, economic, and regulatory hurdles, which is pretty much important. So this is the Northern Lights, as you can see, very famous. And this is the entire setup where you could see the entire facilities, the capture and the transport facilities, and it has been provisioned into ships like this. So these are typically those ships in those docks which actually contain these gases, and these gases are finally poured in through this type of machineries. These are some of these conduits and valves. So and that is how you could see that what would be the type of the provision and the investment made. And finally, in oceans, you could see that these are getting fixed. So this is one of the very successful implementation of CCS projects. The second case study is the Petronova project. Pretty famous. This is one of the large-scale carbon capture and storage project, which is in Thompson, Texas. So this particular project is initiated through the WA Paris generating station. So this is the generating station which is located in Thompson, Texas. And here you could see this is as an outcome of a joint venture between Energy and Nippon Oil and Gas Explorations. And this particular project aims to capture a carbon dioxide emissions from one of the coal-fired boilers at a power plant that use captured carbon dioxide for enhanced oil recovery. And this is routed all the way to West Ranch oil field. If you could see here is the place of the generation, and here is the place where it is routed to. Now, so this has significant key components where the project approximately captures 90% of the carbon dioxide from a 240 megawatt slipstream of flue gas. So this is where it is generated from the thermal power plant, and then using this advanced amine-based adsorption system, it is being pushed to Mitsubishi Heavy Industries. So in terms of transport, if you look at the carbon dioxide is compressed first of all, and then transport via an 82-mile pipeline to the West Ranch oil field. You could see this. So this is the distance, and here there are provisions for storage and utilizations where at the oil field the carbon dioxide is injected into the reservoirs, and this helps in enhanced oil recovery, and this helps also in the permanent storage of carbon dioxide. Over a period of time, over a number of cycles, we concentrate carbon dioxide that gets absorbed over the surfaces and pushed onto the pores, and therefore you have a long-term storage of carbon dioxide. Now look at the achievements here. So here we could actually see that we have uh, uh, we have economic viability, wherein you have the Petronova project getting operational from 2017 has actually become the largest post-combustion carbon capture project in the world at this time. It has a higher carbon dioxide capture efficiency. If you look at, so carbon capture is 1.4 million tons of carbon dioxide annually, and the carbon capture rate is around 90%, which is very, very effective. If you look at the enhanced oil recovery, once the carbon dioxide is injected, it boosts in oil production. You could see the numbers. So 300 to around from 300 to over 15,000 barrels per day is the type of the oil recovery that we are. However, there are a number of challenges here. It could be economic viability, where the process of oil fluctuation, oils have suffered a lot because of fluctuations. There are operational issues here, mm, where the cogeneration capacities have been affected. So there has been outages because of these operational difficulties, and therefore once during this COVID times, May 2022, this was shut for some time, and then it was restarted in 2023. It's because of a very low oil prices where the things were not viable. So this is the plant, and here this is the various utilities. These are the ways in which the carbon is getting captured. So these are various stages, and this is actually the process flow diagram of the flue gas capture, where we could see carbon dioxide of a very high purity getting generated at the end. So for more details, I think we could actually have questions later. Now, so we have covered mostly the technical aspects here. Now let's look at the economic aspects of carbon concentration, uh, capture, utilization, and storage. When you look at the cost analysis, this gives us an idea about several factors that are important, which could be the nature and the type of the capturing technology, the scale of the project, the location, because of a lot of resources and logistics. So these actually are important factors that affect the costs. Now, when you look at the capture costs here, it is around 50 to 100 tons, $50 to $100 per ton, which is mostly to do with the technical and so this is based on the type of technology that is being used and the emission sources. You have transport costs, and then this carbon capture transport via pipelines looks to be more lucrative and economic, where it could stand from $1 to $10 for every ton for every 100-kilometer transport. If you look at the storage costs, the carbon storage in geological formations, which cost around $10 to $20 for every ton of carbon dioxide. So these are some of these real estimates of the costs. If you look at these are the very many ways in which the costs can vary based on the type of sources, where it is high concentration, medium or low concentration of carbon. If you look at the type of the capture here it could be post combustion, pre combustion, and oxy-fuel. Based on the type of the conveyance, which is transportation, whether it is conveyed through ship or pipelines or tanker. And then we have how are we going to store it, whether it is in silent aquifers, ocean, or depleted oil or gas field. So the costs are going to vary. So if we are putting this into mineralization, to products and synthetics, also there could be a lot of costs involved in that. So in these cases, let's look at the type of the funding and the investment opportunities here. Of course, like there are government funding, where United States Department of Energy has already funded around $1.3 billion, and this is mostly to do with building CCUS technologies. There are a lot of private investments where it is important for achieving R&D and CCUS deployment. Well, we have this public-private, this is the government and the industry partnership that is pretty much crucial for scaling up for these type of projects. Now let's look at the economic benefits here. Of course, like when this is boosting a lot of revenue opportunities, which thereby also creates a lot of job in construction, engineering, and operations sectors. So therefore, it has tremendous scope for projects in India. And of course, if you look at the economic growth, it actually boosts the production and the manufacturing sector because of a lesser dependence on fossil fuel and more dependence on the type of carbon that is getting captured. This has tremendous market opportunities, and of course, it suffices to the climate goals. So according to IPCC estimates, if such type of CCUS technologies are not implemented, then it would actually take a lot of efforts. So there could be around 138% increase in the type of the revenue that is pushed in to achieve the CCUS or the type of technologies. So this particular graph gives you a flavor of the different ways in which the carbon dioxide is getting captured. So this is the revenue in terms of $1 billion per year, and this is the type of the carbon dioxide sequestration levels. So if you look at, so here in case of storage and utilization, you have the largest negative investments, which is profitable, and that is how you could see that there's a higher carbon dioxide reduction levels here, and then it tapers down when we have higher entities in terms of these investments in all these other sectors. We'll look at the policy and regulation aspects. So we have these global policies here, and see that Duster along with Niti Aayog have come up with a very comprehensive approach for carbon capture, utilization, storage. So this is actually the policy framework and its deployment mechanisms and the roadmap for India. You could easily download these things from this particular website. This is Clean Energy Ministerial website. So this gives us various methodologies of how do we make sure that at various sectors we are implementing such type of strategies, and not just we are abating carbon, but also rerouting and repurposing this carbon dioxide for other uses. So there are so many different types of different global policies, like the Clean Energy Ministerial CCUS initiative, the Paris Agreement and the International Energy Agency, which gives us the framework guidance and support to implement CCUS policies and regulatory frameworks. You have many different types of approaches at the national level, wherein United States have come up with the CCUS comprehensive regulation scheme. You have European Union's, this is Carbon Capture and Storage Directive that emphasizes on geological storage of carbon dioxide. We have Australian's regulatory framework, which promotes offshore petroleum and greenhouse gas storage act. And there are various types of incentives and subsidies that are being provided today. So yes, Section 45Q tax credit in US, where there's a federal tax credit for, you have any incentives for any provisions for carbon capture, storage and transport. We have UK carbon price support. Today, the UK government actually provides a financial aid to CCS projects via carbon price support. And then we have the European Union Innovation Fund, which gives a lot of funding for low carbon technologies, and there are very consistent grants under Horizon 2020 and onwards for large scale demonstration projects. And of course, in India, we are attempting to put a lot of incentives for industries if we are repurposing or are having a provision for rerouting carbon dioxide into any of these methods. So these are so we learned about carbon dioxide mechanisms. Now we'll have a look at the type of the work that we have been doing on carbon capture, carbon utilization and storage in biomasses. So this is mostly the algal way, where we actually grow a lot of algal strains. And these algal strains are very peculiar is because these algal strains have tremendous ability to sequester carbon both in organic and inorganic form. So here we have this different types of algal strains that have been isolated, cultured for this type of processes. So these are strains which are heterotrophic and mixotrophic in nature. So when we say mixotrophic, they can actually hold on to dissolved carbon dioxide and also can take organic carbon that is present in. So here we have started this experiment way back in 2009. So where we have looked at all these different types of algae carbon that are today basically being pushed as the next level technology, which is at a technology ready level 6 and 7, which is going to be promoted as a commercially realizable technology in industries today. So this is where we have this lab scale shake flask cultures, where we have been able to increase the algal productivity by making sure there's a lot of inorganic carbon, both from flue gaseous sources and from wastewater inorganics, and a lot of organics from wastewater. So these are the various levels at which we have cultured. So it is closed and open cultures, and we have algal towers, and these are the various isolates that we developed over the period of time. So this is the way in which there is a systematic development of scaling up. So these are the facilities at Oregon State University where we scaled up from the bench level to the pilot level. So as you could see, these are concentrated carbon streams from dairy, flush manure units. And here you could see that how we are able to increase the algal productivity, and then we have provisions for the multimodal algal bioprocesses options for municipal wastewaters. So this is a real-time plant that is being operational until today at the Corvallis wastewater treatment plant that is involved in wastewater conversion to algae. So this gives you a carbon dioxide abatement, a biofuel, and also gives a provision for removing the, uh, the nutrients through uptake by algae. So algal carbon dioxide concentration mechanism. So to give you a brief of the mechanisms that are being used today. So as we have been using algae for a very long time for CCUS, so carbon dioxide concentration mechanisms are involving a bicarbonate ion exchange mechanism. So there are three different mechanisms of CO2 concentration. If you look at this particular curve here, so here this is the algal cell, and this is where there's a conversion of bicarbonate ions into carbon dioxide via this anhydric carbon anhydrase enzymes. So this is called the anhydrase pathway. So where there could be several different ways in which, so these are the different transporters within the cell, which is big A1, big A2, split A1, A2, and BCT1. So these are the transporters. And well, we have, this is where the carbon dioxide is converted into carbonates and bicarbonate fixed inside. So these are ways of making sure that the carbon dioxide that is present in industrial flue gases could be incorporated into this biomass and could be later converted into desirable biofuel. So we have the second method, that is the carboxysome encapsulation through rubiscosome, the largest enzyme present in photosynthetic systems that helps in converting the carbon dioxide into carbohydrates. And then finally, we have the third process with the conversion of carbon bicarbonate into carbon dioxide via the anhydrous systems. So we have noticed, so this is the way that we have been growing a lot of algae. And then these are some of the species which have remarkable abilities to take inorganic and organic carbon, Euglena species, and these are the ways in which we have derived biodiesel out of it. So the experiments that we have conducted over a period of time have shown that when we are using various concentration of carbon dioxide into injection streams, that has led to a maximum production of 1.8 times the growth and 2.7 times the biomass densities. So you could see that if we are adding additional carbon dioxide from industrial sources as flue gases into the systems, there is a remarkable increase in the concentration of these type of algal, and therefore there is a higher concentration of biodiesel that we could actually produce. So yes, so this is a mechanism that we have already applied to some of the places in Bangalore. So here we have provisioned such type of reactors at various downstreams of the lakes, and here the wastewaters has a provision for integrating carbon dioxide. So this carbon dioxide in two ways. So carbon dioxide can be initially get into insoluble precipitate carbon bicarbonates and then could be fed, or it could be directly sparged into these cultures by diffusers, where this can actually the particular technology can convert the algal biome, the waste streams, carbon dioxide in inorganic, organic form in waste forms, and the flue gas carbon into different types of products. So this is where we have the entire routine work that was developed for the continuous algal reactor, which is also a recipient of the national award. And these are at various stages of implementation in pre-commercial and commercial levels in India and abroad. So summary, so we have looked at the very process of carbon capture, utilization and surface. We have also looked at how there is a production of a lot of products and polymers and fuels from such type of mechanisms, how this works. And we have also covered the economic policy and other aspects in this algal cells. So because of paucity of time, I'm skipping off some of the things which was very crucial. So in this case, you could see that we have the carbon capture, utilization and storage, where we have made sure that these are implemented at various levels in various sectors. So the frontiers in carbon dioxide technologies, carbon dioxide capture technologies and storage technologies for atmospheric well-being, which we are being promoting, is algal bioreactors, bioenergy with carbon capture and storage. We have enzyme-based captures, where it could be that with an enzyme systems, we could grow a lot of diffused substances which could actually help in addressing carbon dioxide. So there could be direct air capture. We have methods of membrane separation and cryogenic carbon capture. So with this, I thank you very much for a very patient hearing. And so there's a lot of people who have helped us to develop such type of technologies, which are at various like TRL levels. So I would firstly like to congratulate and thank our team who has put a stupendous effort in developing such type of systems in the laboratory at IISc Bangalore. So this is the first of its kind of this pioneering work on algal biofuels, rooted way back in 2008 and 9, where the first ever documented evidence of diatom-based carbon capture and conversion of fuel came into being in our laboratory in IISc Bangalore. I thank my institute UPS Dehradun for providing me with all infrastructure and support for performing this type of studies here. We thank Government of India, MHRD. I also thank the Scale Up Division, which helps us develop the technologies to the next level, which is the Agricultural Research Foundation at OSU, with the help of Hatchlag grant funds through Western and Sun Center. I also thank the projects from the project funding from USDA and IFA USA, NSF Geo. I also thank a lot of collaborators that have helped us in devising such type of technologies, like people from researchers from Berkeley, from INL Braga, from IGDF Netherlands, Tech de Monterrey, Mexico, and DEEC in Australia. And of course, one of the pioneering work was initiated by Professor Richard Gordon, who is at the University of Manitoba in Canada. So out of a lot of relentless efforts, there has been this type of technology that are being developed today, which could be used for large-scale deployment at various places to make sure that we have a substantial amount of carbon dioxide that is getting captured. Thank you very much for a very patient hearing, and I'm very, very grateful to the committee for inviting me for this particular talk on account of the celebrations of the global atmospheric, the World Atmosphere Day. And I thank Ministry for the funding and support, and my institute for all the privileges and the setups that are being developed today with the projects. And the floor is open for questions. Thank you very much.
Thank you so much, sir. You have talked about carbon capture, utilization, and storage, which some of us are very new to this topic, and which has started from 1972 onwards. And due to the condition of the carbon dioxide emission of more than 40 billion tons worldwide. So you have showed us different kinds of carbon capture, carbon utilization, and carbon storage types, and also you have shown current technologies which has been implemented in different projects like Northern Light project, the Petronova project, as well as where you have also implemented in many places in India as well as in IISc. So now we'll take the questions. Please post your questions in the chat box. So there is one question. That's question from Tanuja Joshi. I'll read it out.
Sure.
Good evening, sir. This carbon dioxide can be used by fire extinguishing units also, so that no extra expense is made on the extinguishers. It is just a thought under CCUS utilization part.
Yeah, could you please repeat? I didn't get the essence of the question.
Yeah. So she is asking if this carbon dioxide can be used by fire extinguishing units, so as there will be no extra expense made for the extinguishers. It is a question based on the utilization of CCUS.
Of course, yes. One of the utilities of carbon dioxide after it is getting compressed is a use of CO2 in extinguishing fire. That can be provisioned. Of course, one of this has been already adopted in a number of places. Today, we are with more effective fire retardants, which are effective these days. Yeah, thank you very much. So that could be actually a good provision where it could be that a lot of carbon dioxide could be used this way. Yeah.
Okay, thank you so much, sir. I don't think there are any more questions.
Okay.
Now I'd like to request TVS sir to conclude the session for today.
Thank you, Durga Madhab, for giving an excellent talk on the carbon capture technology as well as storage. And it's interesting to see the role of algae in this whole process. If you have noticed that way back in 2010, I had written a review in the current science on this aspect, some of which you covered today were discussed at that time. And of course, that is the time we also they talked about algae, especially the diatoms, and your role in that is significant. I hope you and your student will take this technology forward and see that we can mitigate the changes happening in the climate and also mitigate the global warming. So,
Of
best
course.
wishes to you for your interesting presentation, and also I hope you will carry forward the research in the same spirit and contribute to the country.
Thank
So,
you very much. Thank you so
so
much.
now you have double power, so you should be able to do much better than earlier time.
Yeah, thank you so much. Thank you very much for the opportunity. I'm very grateful to the entire team. I'm also very much grateful to Professor Ramchandra, under whose stewardship I take up all these projects. I was very fortunate that we could actually get funding from MHRD, DST, DBT, and GTZ. A lot of different funding agents have contributed to the development of infrastructure and laboratories, and that have paved this way for the development of algal biofuel research. So I'm very proud to say that we are among the first ones who have initiated and the algal revolution in India, so as to say. If you look at the type of the documentation of algal biofuels, we could actually see that there is strikingly higher amount of documentation of algal biofuels post the research that we have conducted in laboratory. And as sir rightly told, the initiative taken up by Professor Ramchandra and his various collaborators have helped us in a great way, not just to bring in funding, but also to nurture the technology to the next level.
Okay, thank you, Durga Madhav.
Thank you so much.
Thank you so much, sir. And with this, we come to an end to our very insightful webinar. And on this note of World Atmospheric Day, we have been blessed with a very informative talk. And thank you. I thank both the speaker as well as the participants for joining us today for your active engagement.
I think there is a question from Dr. Gopalakrishnan.
Dr. Gopalakrishna, you can unmute yourself and ask the question.
Is it that he is available now? So I could see a hand raised.
Yeah, we can also see, sir.
Professor Gopalakrishnan, is there a query here?
Yes, unmute.
Yeah, Professor Gopalakrishnan, you can unmute and ask your question if you have any. Well, I think there might be an earlier concern.
I hope there are no more questions then. Thank you to all of you. We encourage you to keep an eye on IISc website and all the social media pages for announcement about further webinars in our live webinar series. You can also visit our YouTube channel NVIS IISc for more informative talks on these environmental topics. Thank you once again for being a part of this event.